Welcome to Independent Aircraft Investigations. My name is Richard Godfrey. Today we are going to investigate Air India AI171 and the first crash of a Boeing 787, which took place just after takeoff from Ahmedabad Airport in India. The Government of India, the Ministry of Civil Aviation, and the Aircraft Accident Investigation Bureau released its 15-page preliminary report 30 days after the accident. The accident occurred on the 12th of June 2025. The report states there were 260 fatalities, 241 on board and 19 on the ground, and there were 67 injuries. The aircraft was destroyed, but remarkably, one passenger survived. The Aircraft Accident Investigation Bureau, AAIB of India, in line with International Aviation Investigation Practice, the ICAO Annex 13, explicitly stated that the purpose of the investigation is to prevent future accidents, not to apportion blame or liability. The report presented factual information collected so far on the aircraft background, sequence of events, the flight recorder data, and technical findings such as the movement of the engine fuel cutoff switches shortly after takeoff. It did not conclude why those events occurred or assign responsibility for them in the sense of pilot error, mechanical failure, or other causes. It did report cockpit voice recorder data, such as a conversation about fuel being cut off, but it did not identify which pilot said what or conclude that either deliberately caused the event. On the 17th of September 2025, the Safety Matters Foundation petitioned the Supreme Court of India with a 460-page document. The petition, in the public interest, was filed under Article 32 of the Constitution of India, seeking an appropriate writ or order or direction to the respondent, the Union of India and others, to make publicly available the complete data retrieved from the crashed Air India Boeing 787-8 Dreamliner, bearing registration VT-ANB, which met with a fatal accident on the 12th of June 2025 at Ahmedabad, and to appoint independent professionals to monitor the investigation, as the respondents' selective and incomplete disclosure of critical information, coupled with the premature attribution of pilot error while overlooking systemic faults, has resulted in a continuing violation of Article 21 and Article 14 of the Constitution of India. Independent Aircraft Investigations brings you the established facts. We provide traceability of all evidence to a source authority. We make a clear distinction between factual data and analytical interpretation. We are not party to the official investigation, and this report does not represent the views of any official body. We operationalise ICAO Annex 13 by embedding investigative discipline directly into the production of each episode. This ensures factual material, analytical work, and narrative outputs remain clearly distinguished, traceable, and compliant throughout the life cycle of an investigation. Aviation news is covered on Daily Airline News with Jeffrey Thomas, As It Happens. This channel is reserved exclusively for in-depth investigations. If you find this analysis useful and want to see future independent investigations, subscribing to the channel helps ensure this work continues. The founder of Safety Matters Foundation is Captain Amit Singh, and I have been in contact with him, and he has kindly shared information in his possession. The Supreme Court agreed to hear the public interest litigation and other related petitions seeking an independent or judicially monitored inquiry, rather than leaving the investigation solely to the Aircraft Accident Investigation Bureau. The court has issued notices to the government and other authorities and sought their responses. And as of the 23rd of February 2026, the court extended time to the centre to file a response, indicating the matter is still active and awaiting further hearings. The Supreme Court has not issued a final decision on the petition. Proceedings are continuing as the court examines arguments about transparency, independence of the investigation, and the disclosure of critical flight data. The Wall Street Journal published an article on the 11th of July 2025, preempting the preliminary report, titled "Pilots Are Focus of Probe into India Crash." The investigation, it says, into last month's Air India crash is focusing on the actions of the jet's pilots and doesn't so far point to a problem with the Boeing 787 Dreamliner, according to people familiar with US officials' early assessments. Preliminary findings indicate that switches controlling fuel flow to the jet's two engines were turned off, leading to an apparent loss of thrust shortly after takeoff, the people said. Pilots use the switches to start the jet's engines, shut them down, or reset them in certain emergencies. The switches would normally be on during flight, and it is unclear how or why they were turned off, these people said. The people also said it was unclear whether the move was accidental or intentional, or whether there was an attempt to turn them back on. If the switches were off, that could explain why the jet's emergency power generator, known as a ram air turbine, or RAT, appears to have been activated in the moments before the aircraft plummeted into a hostel for medical students in Ahmedabad. No final consensus exists until the final AAIB accident report, which is typically published many months after a preliminary report and after a thorough analysis. The Supreme Court described the selective leak and piecemeal publication of information that suggested pilot error as unfortunate and irresponsible, and damaging to the integrity of the investigation. The bench emphasized that such leaks fuel misleading media narratives rather than focusing on facts under formal investigation procedures. On Daily Airline News with Jeffrey Thomas, we have published 120 episodes on the Air India crash. And today we present an alternative explanation to the pilot error narrative. And this episode is dedicated to the memory of the Air India 171 victims. Further to the investigation on the Airline News channel of the Air India 171 crash, many pilots, engineers, and experts including some currently working at Boeing and at Air India, have shared their insights. We presented the evidence that allows a determination of the root cause of the crash on the 12th of June 2025, costing the loss of 260 lives. There are a number of key observations. Number one, when the crew advanced thrust levers at the start of the takeoff roll, the engines responded, but the acceleration was slower than normal, and it took longer than normal to reach V1 at 08:08:33 UTC. Number two, after V1, the acceleration was normal for 9 seconds until 08:08:42 UTC, when the preliminary report records the maximum airspeed was achieved and thrust was lost on both engines within 1 second of each other. This point in time is 3 seconds after liftoff at 08:08:39 UTC. Number three, the RAT was deployed, and the preliminary report records that the EAFR data indicates both engines' N2 values passing below minimum idle speed, and the RAT hydraulic pump began supplying hydraulic power at about 08:08:47 UTC. Number four, the Boeing 787 functional schematic for engine thrust crew alerting shows that if the thrust resolver angle, TRA, becomes invalid, the engine electronic control, the EEC, defaults thrust to idle on both engines. The engine indication and crew alerting system, ICAS, will display the message EEC ENG thrust low left and right. Number five, the captain is reported as having communicated to the air traffic control, the ATC, a mayday and stated thrust not achieved. And finally, the sixth observation, the engines were both successfully relit, but insufficient thrust was achieved in time in order to save the aircraft due to the low airspeed and low altitude. Now, there are 5 key events. Number one, there was a fault reported on the previous flight, AI423, at 05:29 UTC, just before touchdown in Ahmedabad. Number two, ACAR's message cluster occurred at 07:52 UTC, and that was just after pushback, engine start, and 5 minutes before the taxiing started. Number three, during the takeoff roll, the aircraft reached the decision speed V1 at 08:08:33 UTC. Number four, the air-ground sensors transitioned to air mode, consistent with liftoff at 08:08:39 UTC. And at about 08:08:42 UTC, the engines N1 and N2 began to decrease from their takeoff values. Let's focus on the ACARS messages. The message was an EFFDE, Engine and Fault Fleet Data Extract, which means it's a routine download from the aircraft's onboard maintenance system, the CMC. Decoded items into plain English, there were 7 active and 1 latched CMC messages. The first one, DB24, BPCU gateway ops right and left. 2 different bus power control unit messages with 2 different IDs. And that can be put down to 2 separate fault conditions from the same equipment. The word gateway suggests a data bus communications issue. Number 2, DB27, FCM, ops right, left, and center. Flight control module items with all three channels referenced means something common to all three: shared comms network, shared power feed, shared gateway, or a central data concentrator. You need the full CMC drill down to know whether it was transient, dispatchable, or a no-go for flight. The third message, Captain's EFB electronic unit. The electronic flight bag on the captain's side had a hardware issue. Number 4, DB42 GPM, General Ops right 4 and left 1. The generator power module, one on the right side, Unit 4, and one on the left side, Unit 1. Number 5, DB29, high diff ops right, a right side hydraulic interface related fault. Number 6, DB38, WVV ops 2, a water vacuum valve, WVV, which controls vacuum flow in the lavatory waste system. And number 7, L aft zonal dryer, a latched fault in the aft zonal dryer, perhaps of an air drying subsystem used to manage moisture in an equipment or ventilation zone. If any fault had an operationally significant impact requiring crew awareness or crew action, it would typically appear on ICAS. However, some dispatch limiting or maintenance detectable faults may only exist in the CMC EFFDE data and still be a no-go under the minimum equipment list, the MEL, unless deferred. It is possible that none of these CMC messages met the persistence or alerting thresholds required to generate an ICAS message. Certain faults, depending on their duration, recurrence, or associated system redundancy, could still have required MEL action prior to dispatch. The 0752 UTC snapshot, post-engine start and pre-taxi, shows a clustered set of CMC messages spanning electrical power, control and generation, the BPCU and the GPM, the flight control computing, FCM, the hydraulic interface, and utility moisture-related items like the WVV or the aft zonal dryer. Without CMC drill-down data, these entries cannot be characterized as transient versus persistent, and crew enunciated versus maintenance only, or causal versus incidental. However, the cross-domain clustering and the presence of gateway wording makes the snapshot suitable for correlation by investigators against power transfer events, data network health, and any documented evidence of moisture or contamination affecting systems located in or routed through the aft EE bay. The throttle resolver angle, the TRA, from the Boeing 787 functional schematic, engine indication and crew alerting system, ICAS message logic, figure 73-21-04, the message EEC engine thrust low can be triggered by the following path: a TRA invalid and thrust defaulted to idle, and that will bring EEC engine thrust low. The EEC, the electronic engine controller, no longer trusts the throttle resolver input, usually due to an open or short circuit in the resolver wiring. The resolver to digital converter might have had a fault, and an invalid or inconsistent TRA signal between the channels. When the TRA becomes invalid, the EEC loses its commanded thrust reference. So by design, it defaults the engine thrust to idle to prevent unintended power increase. The schematic shows that the TRA invalid and thrust defaulted to idle feeds directly into the EEC engine thrust low logic path, bypassing the slower 10-second engine not accelerating condition. This means the message can appear almost immediately once the fault is detected, and the EEC transitions to idle default mode. The EEC engine thrust low ICAS alert indicates that the engine's actual thrust is significantly below the commanded value. If triggered by TRA invalid, it points to a control channel or input reference failure, not a fuel or mechanical fault. The absence of a fuel or mechanical fault aligns with the observation that the engines were both successfully relit, but insufficient thrust was achieved in time to save the aircraft due to the low airspeed and low altitude. It was only 3 seconds after takeoff. If both throttle resolver angles, TRAs, were invalid, leading to thrust defaulted to idle on both engines, the crew would see the ICAS message, engine thrust low, on both engines, left and right. And that condition corresponds exactly to what the captain described over the radio as thrust not achieved. Now, each GE Annex 1B engine on the 787 has a dual EEC channels, A and B. When TRA input from the throttle quadrant becomes invalid or inconsistent, the EEC cannot determine commanded thrust, so it defaults the engine to idle as a fail-safe mode. The fuel metering valve, the FMV, drives to the idle stop, regardless of the throttle lever position. And simultaneously, the ICAS message EEC engine thrust low is triggered by the logic path we have highlighted, TRA invalid and thrust defaulted to idle. The message tells the crew that the EEC is producing less thrust than commanded because it has lost the valid throttle input. Let's have a look at the timing implications. At 08:08:33, V1 was reached, but late. The roll phase acceleration was sluggish, but not idle. The engines were making thrust, just less thrust and slower to build than expected. This fits the branches of the functional schematic describing lack of engine acceleration, which can transiently set EEC engine thrust low with short set and clear timers without TRA being invalid yet. At between 08:08:33 and 08:08:42, there were 9 seconds of normal acceleration, including 3 of those seconds when the aircraft was airborne. The engines at 08:08:33 did respond normally to lever commands. That means TRA was valid and the EECs were honoring the commanded thrust in this window. If an EEC engine thrust low had been set during the early roll, the schematic's 5-second to clear path could explain why it cleared once acceleration normalized. At 08:08:42, 3 seconds after liftoff, a new event occurs that removes commanded thrust. Most plausibly, TRA becomes invalid, pushing both EECs to thrust defaulted to idle. And from the cockpit, this is when thrust not achieved becomes obvious in the climb. Now, let's consider the engine electronic controller, the EEC. The fail-safe behavior of the GENX1B EEC is described in this section, both under normal conditions and when the data communication with the Common Core Resource CCR is lost. First, let's look at the normal CCR EEC link function. On the 787, each EEC for the GENX1B engine communicates with the aircraft systems through the Common Core Resource, the CCR. And it does so via dual redundant ARINC 664 AFDX data buses. Through this link, the EEC receives throttle resolver angle from the throttle quadrant module via the FCCs, the air data pressure, altitude, Mach, total air temperature, aircraft configuration and bleed anti-ice status, weight on wheels and flap and slat position and other control surface signals, and the mode and thrust limit requests, for example, TOGA, climb, or cruise. The EEC also sends data back, engine parameters, thrust rating status, etc., to the CCR for display and flight control functions. Now, what happens when the CCR to EEC link is lost? There's a data link failure. If the EEC loses communication with both redundant CCR links, the EEC immediately enters a fail-safe mode. This state is treated as a major fault because the EEC can no longer receive trusted data from the airframe or valid thrust lever positions. The throttle resolver angle inputs are lost. The EEC cannot determine the pilot thrust commands, and the thrust mode limit signals are lost, and the EEC cannot interpret what thrust regime is intended. Air data inputs are lost. The EEC cannot safely schedule fuel flow or control limits like overspeed or over temperature. So what is the EEC's protective response? To prevent an uncommanded thrust increase or over-fuel condition, both EEC channels A and B revert to a fuel cutoff protection mode. A commanded fuel flow to zero in the fuel metering valve closing, engines begin to wind down, and no restart possible until valid CCR EEC data link is restored. This is a deliberate design feature. It's safer to lose thrust than to risk an uncontrolled or asymmetric thrust event. The Boeing and GE documentation references are important. While the detailed fault logic is not public in full, this behavior is documented in several technical references. The Boeing 787 Aircraft Maintenance Manual, the AMM, Engine Electronic Controller Description and Operation, the GENX1B Engine Maintenance Manual, the EMM. EEC commands engine shutdown upon loss of valid aircraft data or invalid thrust lever angle inputs. And the Boeing Fault Isolation Manual, the FIM, the CCR EEC communication fault is a condition that results in EEC commanded engine shutdown. The Boeing Fault Isolation Manual, the FIM, CCR EEC communication fault as a condition that, and I quote, results in EEC commanded engine shutdown. The 787 has a highly distributed electrical system designed around 4 main AC buses and multiple DC conversion and distribution buses. The DC power system is supplied by TRUs, transformer rectifier units, that convert 235-volt AC from the AC buses into 28-volt DC for the DC buses. The key DC elements are the left and right main DC bus, the left and right battery DC bus, the hot battery buses for essential and APU start functions, and the DC tie bus used to cross-connect sides under failure. In flight, each side's main DC bus is powered from its own true. But if one side loses true power, a DC tie contactor closes after a short intentional delay to connect it to the other side's live bus, restoring DC power redundancy. The design assumes typical failure modes, such as open circuits or loss of TRU output, or moderate load faults, where isolation and tie logic protect the healthy side. But in the case of a massive low impedance short on the primary DC bus, which is a 1 in over 1,000 million flying hours safety issue, the primary bus voltage collapses immediately, close to 0 volt. The system control logic detects the loss of DC voltage and roughly after 1 second commands the DC tie to close to bring power from the other side's bus. However, since the short still exists physically on the primary bus, closing the tie contactor instantly transfers the fault to the secondary side. The result is a propagated short, and both buses go down and almost simultaneously, separated by the tie delay. This effectively defeats the redundancy. A single physical short can collapse both sides' DC powered distribution within seconds. The 1 second logic delay between tie closure is intentional. It's designed to prevent nuisance tie-ins during transients from the TRU load changes and allow system fault detection and isolation time, and ensure orderly sequencing of automatic bus transfers. However, the logic cannot distinguish between a benign bus voltage loss and a catastrophic bus short. The automatic bus tie vulnerability isn't unique to the 787. It's a known issue in common bus DC architectures with automatic cross-tie logic. However, it's particularly sensitive on the 787 because the aircraft uses large DC loads for brakes, control actuators, and galleys, etc. The DC buses are physically close in the EE bays. The DC tie contactors are high capacity, hundreds of amps continuous, and thousands of amps in surge. Boeing has mitigated the operational risk through monitoring, improved circuit protection, and isolation logic. But the underlying architecture, a DC tie capable of linking 2 buses under low voltage conditions, inherently creates a potential shared fault path. To fully eliminate this, Boeing would have to replace or interpose the DC tie with isolating bidirectional DC-DC converters, or redesign the fault detection logic to never tie buses automatically unless the fault is confirmed as being non-destructive. When both engines are shut down or below idle, the main generators, the two variable frequency starter generators, the VFSGs, go offline, and there's no 235 volt AC. The permanent magnetic alternators, one per engine, are offline. They need rotation to produce power. And the permanent magnetic generators, three in total, are not producing power when the core rotation is less than 7% of N2. And if the APU is also unavailable, the airplane has no AC or DC power from any normal source. And battery power alone is insufficient to drive ignition and starter valves or essential control channels for more than a few minutes. When engines shut down, the pilots will receive a whole raft of ICAS messages. The main battery, an APU battery with a dead short on both DC buses, would take out both the main battery and the APU battery. And each battery feeds its own battery bus, isolated by a battery contactor. The battery buses backfeed the hot battery bus and can support DC essential bus. If a DC bus fails, the DC tie can automatically connect the other side after 1 second. Each 787 battery system includes a battery contactor relay opened by the BCU on fault. The BCU, the battery control unit, has protection for overcurrent and over temperature. There are current limiting resistors and solid state protection within the DC distribution center. However, those devices react in tens of milliseconds. They are fast, but not instantaneous. A dead metallic short in the bus trunk or connector can create currents well above safe limits before the contactors open. The question remains unresolved whether the smoke seen on rotation was the main battery or the APU battery suffering a dead short. Now, the engine igniters had to wait for the AC power from the RAT to come online. The FADEC functions under its internal lithium-ion battery backup, ensuring uninterrupted operation. Engine relight sequence started only 10 seconds after the RAT deployment, when the AC power from the RAT came online. The relight sequence was successful in both engines, but the time to develop full thrust will take longer than 60 seconds. And with only a 32-second flight in total and 10-second delay before starting the relight sequence, this left too little time for sufficient thrust recovery. We have attached a link to an Excel spreadsheet with the detailed timeline of events. And all events timing referenced in this analysis are drawn directly from the accompanying analytical spreadsheet, which includes a column marked source, identifying the origin of each data point, either from the AAIB India preliminary report, the ATC communications, the airport ground radar, from the Flight Radar 24 ADS-B data, or the airport CCTV footage. This information was part of the original evidential data set and underpins every time correlation used in this analysis. By explicitly noting these independent sources within the main report, the provenance of data is transparent and verifiable, clarifying that the analysis rests on cross-sourced empirical evidence rather than on derived or inferred timing estimates. There are two failure chains which are important that can cause a CCR to EEC link failure. A LVDC massive short. A massive short on the 28-volt DC bus due to an internal DDC failure, distribution harness short, or load side short. A voltage sag or protective trip affects avionic power. Let's have a look at the failure chains. There are two failure paths that can cause a CCR to EEC link failure. The first is an LVDC massive short, and the second is an HVDC cooling failure to either the forward or the aft EE bays. And this single point of failure was predicted by MIT in a study first presented in 2016. MIT described the thrust control malfunction, and they also describe how that can cause a dual engine flameout. The LVDC and HVDC are separated, but both the LVDC and HVDC have automated bus tie capabilities as redundancy backup in the event of a failure. If on rotation of the aircraft, the water damaged the power panel P700 or P800 in the aft EE bay, providing HVDC power to the E5 and E6 equipment racks, then cooling to the forward and aft EE bays would cease. If only one HVDC side failed and the HVDC bus tie successfully backfed, LVDC might have survived. Then you'd need an additional short on the remaining side or a tie lockout to explain a full CCR power loss. A pure cooling only path, the HVDC fans off CCR overheat, is too slow to explain an immediate rotation event rollback. Cooling explains later degradations, not the initial dual rollback. The smoke seen on rotation is evidence, in my view, of an LVDC massive short. And the LVDC massive short is the direct electrical cause of the CCR to EEC temporary data link. The engines automatically reduce to idle when a temporary fault occurs in the digital link between the aircraft's central computer, the CCR, and the engine electronic control, EEC systems. This link carries the thrust lever position information, known as the thrust resolver angle, which tells each engine how much power the pilots are demanding. When that information is lost, the engine control systems automatically set both engines to idle as a protective measure. Once the connection is restored and valid data is received again, the system automatically attempts to restart the engines. Both engines were successfully relit, confirming that the temporary fault in the digital link was resolved. Even if the cause of the communication failure was a short circuit in the aircraft's DC electrical system, the engines can be restarted using AC power from the ram air turbine. which supplies the essential electrical buses during such an event. Each engine electronic control has its own internal power conditioning system and a small lithium cell that preserves the processor's memory and logic state when both engine and aircraft electrical power are lost. This ensures the FADEC can resume normal operation as soon as power is restored. The pilots can initiate a manual relight by cycling the fuel control switches, but this will only take effect once the RAT has deployed and electrical power has been restored. In conclusion, all the observations and key events on the Air India Flight 171 can be explained with this alternate explanation. The causal chain and the root cause have both been determined. What happened on the runway, at rotation, and during the initial climb has been described. Why both engines shut down and how both engines were successfully relit has been detailed. Tragically, there was too little time and airspeed and altitude to save the aircraft. The interplay between water ingress into the equipment electronics bay, the electrical system, the engine control system, in the more electrical architecture, the MEA, of the Boeing 787 have been analyzed. If the aircraft had undergone its 12-year D-check or a substantial retrofit program earlier, this accident may never have happened. There is some evidence of deferred maintenance on the VT-ANB aircraft, and despite regular line preventative maintenance, the amount of corrective maintenance piled up. As an alternate explanation to pilot error, we have presented that the pilots were trying to save the aircraft. They succeeded in relighting both engines and almost made it to an emergency landing on a road next to the medical hostel. They were only a few seconds too late.